Good afternoon. I'm always slightly petrified when I get this large an audience. For those of you who've actually read through the entire blurb in the schedule and gone, oh my God, how is that going to fit into 30 minutes? I have to explain it was originally submitted as a workshop, and due to some rescheduling, it ended up as a conference session instead. So I am not going to cover all the stuff that's actually listed. I'm probably not even going to get through half the stuff, and that's because I'm probably not even going to get through the slides I've got with me. But we're going to go quite fast. I'm going to try not to do my normal trick of rambling about absolutely everything except what I'm supposed to be talking about. That may or may not work. And we're going to talk about building machines in software, which is a subject I've been obsessed with pretty much since I first realized that you could make sort of the insides of software look like machines. And which I don't think enough programmers spend enough time wasting time on playing with these ideas. So, and there's going to be C code. And this talk is the proof that C can be a rapid application development language, because most of the C code I wrote in 2 days, and it just seemed to work, which means I've either become phenomenally good at C in the 6 years I hadn't used it, or the things I'm going to show off are actually really simple, so nobody should be worried that they're not. So this is a talk about virtual machines, and virtual machines means many, many different things to different people. Everybody here will have used some kind of software virtualization at some point. You want to run old Windows games on your Mac, you're going to use something like Parallels or Fusion, and you've got a Windows box and you want to run Linux dev chain, you probably have got VirtualBox installed to do that. But this is not a talk about that. It's a fascinating subject, and it does sort of cross over occasionally with what we're going to talk about today. But it's a much deeper rabbit hole than the one that I think we can fit into 30 minutes. This is also not a talk about hardware emulation, although in an odd sort of way it is. Because a lot of what we're going to talk about are ideas that apply if you're going to emulate hardware. And I had to stick this particular slide in because this is Doom playing on Open Riscos in a web browser with a full hardware emulator for the box written in JavaScript, which I just think is so awesome, with a full network stack and everything. And this down here, I used to be a Newton user when they stopped being fashionable and became dirt cheap on eBay, because they're brilliant bits of kit. If you've got something like about 1.6 gigahertz of modern ARM core, you can just about run Newtonos in an emulator called Einstein, slightly slower than you would ever get it to run on a very, very old ARM Hobbit chip. So I thought I'd stick that in just because they're bits of kit I love. And part of the point of looking at machines as inspiration for things to do in software is actually there are machines you love and there are machines you hate. And it's inspiring to understand why you love or hate them. I've used the word inspiring twice, and that's not like me. So this isn't about hardware emulation, but sort of it overlaps. We're really interested in abstract virtual machines today. These are your traditional JVMs, your .NET infrastructures. For those of you who've ever played with functional languages, your SECD virtual machine, which is kind of like the god of how to implement functional languages. Your fourths, and even your Cs, because C does have a virtual machine. It's so damn primitive, we don't think about it. So this is a talk about abstract virtual machines, and it's inspired by hardware, by the idea of discrete components, of processors, of storage, of communications, all of which are actually not that dissimilar to the inspirations for why Go is the shape as a language that it is. The interesting thing about software machines, and having invoked functionality back there, the great thing about software machines is they're stateful. Much of the real world is stateful. I spent many years as an embedded systems programmer. State matters. If you take state away from things, suddenly they don't have any identity anymore within the context you want to use them in. A software machine needs to be timely. It should do something in the time that you want it done in, give or take. The give or take is always important. Stateful in that it maintains that state, you can duplicate that state, you can replicate that state. And scriptable. There's no point in having a machine that you can't add complex behaviors on top of yourself. Ever since the first Jacquard loom, people have been writing programs to make machines do things beyond what they were intended for. And that's, yet again, an interesting thing to try and get in your own software. So I apologize for the really dodgy drawings in here. I did these in a hurry in April, and I always swore that I'd do a more modern version of them that was really nice and pretty, and yeah. It turns out I don't care so much about the appearance of the diagram as I do about other stuff that I was obsessed with for 4 months. So this is basically a very abstract virtual machine describing the average box that you program on. We have a CPU with some registers that maintain local computation state. We have some stacks. Most machines, that means just one stack, but in principle, you can have several. We have buffers that talk to whatever persistent storage we've got, and also that talk to any network connection. And then we have some kind of CPU cache that either holds data that's been brought in from a heap memory somewhere, or holds instructions that we are going to execute. And the numbers are a rough estimate of how fast these various components are in seconds. So inside a CPU, it's not unusual on modern hardware to be thinking in terms of this instruction takes a nanosecond, which for those of you who want to visualize that in some way, and this is completely not to scale, but to a physicist, a nanosecond is about that far, because that's how long it takes light to go that far. As you can see, chips, things go much shorter distances, so if we ever you've got a lot of space yet that we can still use before we've used up our nanosecond. Talking to actual local cache memory is incredibly fast. It's on the order of the same addressing speed, sometimes an order of magnitude slower. Buffers, likewise, because they're local memory to the processor. But once you start getting off towards heap memory, those big objects that in an object-oriented language you've got stored in a garbage collector that might generationally move them about, you just lost 2 orders of magnitude. You're 100 times slower to do anything with those than you are in your processor. Once you move over here into persistent storage, you're now 10,000 times slower. And if you're using magnetic drives, you're 10,000 times slower, and you've also probably got a 4 millisecond wait time between requests. If you go down to the network, you're now 100,000 times slower for an awful lot of things. These are very approximate. They change. You can build hardware that gets around these for particular purposes. But it's interesting to think about the different timings involved. Now, we're going to start off by looking at memory. And I spent a large chunk of yesterday absolutely panicking that the piece of code I wanted to show off wouldn't work, because I was going to do an uber-brilliant piece of reflection and unsafe that would take any arbitrary chunk of memory and convert it into any other arbitrary chunk of memory. And 4 years back, my code for doing that worked, and then some horrible person on the Go team fixed the reflection library, so mad shit like that wasn't possible anymore. Which obviously is a great personal slight. The point of memory is it's somewhere we're going to store data, we're going to store instructions. We want to have some kind of addressing mode to get at it. We're going to have some kind of protection mechanism. We're not going to talk about the addressing and the protection today. Those are, yes, let's have a 20-minute breakout session and let's see what mad ways of saying you're not allowed to write to this byte we can come up with. But we have 4 basic models of memory that we can play with in any kind of processor. So the traditional one we're all used to as programmers is the von Neumann model. We've got a stack coming up from the bottom, a heap coming down from the top, and a higgledy-piggledy selection of data and code all the way through the heap. The Harvard model is, for anybody who's done much embedded programming, there's a number of very nice microcontrollers that insist on using the Harvard model, because it allows you to have a ROM and RAM separate from each other, and you only have code in ROM, you only have data in RAM. And effectively, the Harvard model prevents you from doing horrible little buffer overrun attacks that accidentally put naked functions in the middle of chunks of data, that once they're run over the buffer, suddenly turn into code. Or you could do what Intel do and have an NX bit, XD bit, I can never remember. They've got a bit anyway, so that just says this page is protected, don't do that. This is the 4th model of memory is quite an odd one, because it's 2 different stacks. And 4th doesn't really have a heap. It has a dictionary that sort of could be anywhere in a heap. It could be on disk, and it doesn't care. It's just a whole set of pointers to other pointers. But it shows you that you can actually split out a lot of the things that happen on the stack in the von Neumann system, where you've got data and return and control flow all intermingled. You can actually separate those out. And therefore, you can ultimately come up with a hybrid model where you've got data and code separate, and you've also got immediate data on the stack and control flow on the stack, all separated. And that's something you can only do in software, though, if you're on most processors. And that's another reason why suddenly it's quite nice to be able to suddenly go, well, what's the machine I would like to program for? Because you can write code that will enforce these guarantees in all kinds of horrible ways, and, depending on how you want to think about it. So we're going to start off with something that's a very simple bit of code. It does use reflection. It does use unsafe. And basically, we're just going to create a heap. So for our purposes, a heap is a chunk of memory that's contiguous, it's word-aligned, and it's byte-addressable. Now, it's going to be word-aligned, and it's also going to be byte-addressable, instantly tells us that this thing is two different identities. It is, on the one hand, a slice of uint pointers, because then you get automatic word alignment. But at the same time, I have no idea why that's coming out quite like that. It's certainly not the resolution the slides are at. But the great thing about it is you also want to have a byte slice that exists across exactly the same place. So you've got a heap that's, on the one hand, these uint pointers. On the other hand, you can write to individual bytes. And to do that in Go is actually incredibly trivially simple. The version I was going to write yesterday would have been absolute hell if it worked, and very difficult to talk about. But this is very simple. We just need to know what the types for a byte slice, our memory type, and also we need to know how many bytes are stored in the memory, because uint pointers will be either 4 or 8-bit bytes, depending on your hardware. And once we've got that, we can do some very clever tricks manipulating a slice header from the reflection library to be able to quite happily create new slice headers that point to the same data as the slice header that's already for the uint pointer slice. And this kind of manipulation was one of the first things I worked out when I was first working in Go, because I was trying to implement a fourth. The fourth standard actually requires that the stack can both be 32-bit floating point numbers and 32-bit integers. And Go's native types don't like that, and if you split the stack and have two different data type stacks, you sometimes run into very valid, reasonable fourth programs that can't run, because they expect to use this as a floating point number in one moment, but they reuse it in an integer context in another. Now, these programs are not necessarily sane, but they tend to be device controllers. So, and there's not a lot of sanity in that world, in my experience. So I've come up with a very simple API. We want to be able to overwrite a memory buffer with something else. And we can use a nice little type switch so that we can actually say, give me a memory buffer to write over this memory buffer. Fine, straight copy. Oh, you gave me a byte slice instead. Fine. I'll convert that over and do everything necessary. I've introduced a serialized function that actually will give you back a duplicate of the data as a byte slice. And this is quite handy for interacting with I/O readers and writers. And then I've added in a bog standard, I want to actually look at this thing as bytes. With that, I can now basically write pretty much any memory style system I would want to put in a virtual machine, because I've got the basic plumbing there. If I want to be able to address all of this in terms of ints, fine. I now put in a little bit that does the same manipulations, but it uses an int type. And you can there's a couple of places you could generalize this and pass the type you wanted to use it and things like that. But it does, of course, use reflection, and it does, of course, use unsafe. And this is one of the few genuinely valid uses of unsafe, is these kinds of manipulations. Certainly, if I see it in other code, I start to worry, even when I've written it. So here's a little program that just basically shows this memory working. So I've set up a memory consisting of 2 memory cells. They're both automatically blank. And then I've decided to see, well, what does that look like if I look at that as bytes? And if I take a copy of it, what do those bytes look like? And then to prove that I can now monkey around with the bytes, and I can address the bytes directly and see how they changed, but I can still get at my serialized copy and see the original. And then this down here is just me basically overwriting an 8-byte slice that just counts down from 8 to 1. Yeah. Apart from the fact I like green pixelated text for historic reasons, it's not really a very exciting example. So there's another type of data type that's very, very useful for memory when you're building VMs. And this is basically stacks. And there are 2 essentially ways of doing stacks. There's the way that processors themselves do stacks, which I refer to as an array stack. And that's just basically a big chunk of memory that's assigned to being a stack, and there's a stack pointer, and it goes up and it goes down. And they're quite fast for manipulation. They're slightly error-prone, but the same is true of the other method, because it's very easy to get the stack manipulation counts wrong, because it's just lots of tedious +1s, -1s all over the place. And for more complicated things where you need to get things 2 levels down, and it's just, every fourth program will tell you stack handling is the worst bit. And we're also going to look at something I've mislabeled it here. I called it a spaghetti stack, because when I wrote this slide, I was in a bit of a hurry. It's actually called a cactus stack normally in the literature. This is how functional programmers do it. This is a functional data type. And we're going to go through the code for these, and I'm going to try and do it quick. I doubt we're going to get much further, but we'll see. So an array stack, we've got a fixed amount of memory. We can grow and shrink it using realloc calls. And we've got a stack pointer, which is basically an offset into the array. And as I said, C is a fast language to dev in, it turns out. And I'm a much better C programmer for having spent 6 years writing Go than I was before, because Go's slightly closer to C than Ruby. And C really didn't like me trying to inflict Ruby on it, whereas it does like me inflicting Go. We've got a few things. We have to handle mallocing. And at some point, we have to care about the stack manipulation. And that's about it. Very simple implementation. We can do the same thing in Go. The code's a little bit shorter, not hugely in a direct port. We don't ever actually have to do an allocation, is one of the nice things, because obviously empty slices are automatically nil, and nil slice is an empty slice. Apart from a weird case where if you try to index into a nil slice, you'll get a kernel panic. I can't think of anything else about them that needs thinking about. So the first thing we can do, we've got all of these error codes that we were returning in C, because in C, if we didn't return the error codes, we had no idea what was going on. But we can make all of those disappear in Go, because we don't really need them, because the one exceptional case that we're ever going to run into is the, oh, look, it's a nil slice, and I've indexed somewhere in it, and I've got a kernel panic, which is, a stack itself, when it gets empty, will just be empty. So yeah, and also we can, instead of having any kind of structure to handle it, we literally just have the stack is a slice of int. It's quite nice. Spaghetti stacks are sort of a bit more complicated, or cactus stacks are a bit more complicated. So yet again, it's not going to require initialization, because I hate having things that have to be explicitly initialized if I can avoid it. I think one of the nice things about Go is by default things are initialized to their 0 value. And if that 0 value can be a nil pointer, then a nil pointer isn't going to explode at you later. Fingers crossed. We can do automatic stack growth on push, but in C, we'll potentially leak memory if we do a pop. So let's have a look at this. So yeah, oh my God, we contain some data. We got a pointer to the next stack cell. This is basically just a singly linked list. I spent years hating these. I thought that they were absolutely useless. What's the point of a singly linked list, I used to think? So I save 4 bytes of memory. I'm sure I can just do something with compression or get around that. And I was at a talk about 3, maybe 4 years back at Strange Loop, a guy called Scott Volker, I think his name is, and he just gave this really fascinating talk about implementing functional data types. Because that's a big functional head sort of conference, and it was nice to have somebody else who's more practical engineering side say, well, you can actually implement these in other languages. I can't remember what language he did. And I suddenly started to look at them with a whole different eye. And as a result, I like to use functional data structures now if I can find any kind of excuse for it. So we've got the same basic primitive API that you would expect. We have a push, we have a pop. We need to know the depth of a stack from time to time. We unfortunately also have a garbage collection call. Now, our garbage collector isn't really doing anything useful. This is just sort of a stub for where garbage collection should happen. But otherwise, you are going to end up with a whole pile of pointers dangling all over the place to data that's never going away, because that's part of the point of a functional data structure. The data doesn't go away unless you garbage collect it, i.e. it's gone out of scope for everything in the program. And it's sort of, it's an ugly bit of code, but the example does demonstrate, though, that our GC call does actually reduce the depth of the stack. So, yeah, this is actually being used to do something. Now, unfortunately, when I put together this slide here, and I randomly filled in some numbers, it didn't occur to me that any of these 3 columns of numbers would coincide. But unfortunately, in my example program, further as we go through, you'll find that, yes, they do. We get 5 items that sum to 25 and 3 items that sum to 25. And the first time I looked at it, I thought, why are they both coming out 25 without looking at how many items were involved? And it's just like, yeah, they are genuinely doing it with different data. It's a bad example. We can do a Cactus Stacking Go very easily. We don't have to do any garbage collection. The garbage collector does it for us. One of the really nice things about Go, when you're doing system-level programming, is it's got a garbage collector. And one of the really awful things about Go, when you're doing system-level programming, is it's got a garbage collector. So if this garbage collector could be cost-free to garbage collect, I would be so happy. But it gets close a lot of the time. So first off, this is a very boring straight port. So yet again, we've got our stack structure. We're doing some stuff on the pointers. We've got push, pop, depth. Already, you can see it's... go back one. Oops. Oh, well, forget about it. I'm not always best in control of a clicker. It's a very short program in total. It's very easy to implement these in Go. First thing we can do to make this even more functional and make our functional programming friends happy is, of course, we can get rid of working on the pointers to the stack cells. Now, they're basically immutable. So that's nice. We can also monkey around a little bit. I can't remember why I chose to do that, so I'm going to skip it. It's doing something useful. These slides are all going to be online, so... I can't always remember why I put things in. It's obviously related to that one, so we'll ignore... Oh, yes. So we've got some pushing going on and stuff. Boring. Maps. Now, I didn't think you could really do a stack implementation without also showing how to do a map implementation, because if you're actually building VMs in C, you're going to need some maps. There's all kinds of places where you're going to want to have maps between one kind of data to another as part of caches and things like that, because if you're going to write a cache, it's saner to write your cache in terms of a hash map than it is to do what processes do, or often try to do, and write them as sort of an array that's pretending to be a hash map. You know, tagged memory has been around for a long time, but it's alarming how little hardware uses it. So we've got a C map, and I've broken this into 3 slides, because it turns out there's actually 3 bits to a hash map. There's an associative array, which anybody who's ever read a book on Lisp, it will have been the first chapter. This is how you do an associative array. This is how we make sure that oranges and apples are the same thing. And associative arrays aren't really very interesting data type, because they're just a singly linked list with 2 items in each of the cells. You need to do a search, it turns out. And I think I might have created a new innovation here by actually turning this into a separate type, because I've yet to find an example of any code where people write their maps this way. And I only broke this out because I thought, my God, I can actually understand the algorithm if I do that. Whereas otherwise, it's like all these pointers all over the place, and it makes no sense why they're doing what they're doing. So you need a search, and basically this is a very dumb search. It just maintains a little cursor and a memo for the last cursor position, and you move through. It's not very exciting. And this, unfortunately, is the code for map itself, which works on top of that. So the thing about a map is, if I'm working in C, I'm going to say, I'm going to give this slice, this array of space, and each element in it is going to be one of these associative arrays. Right, so each one's the head of an associative array. And then I'm going to say, when I store some data, I'm going to have a hashing algorithm that figures out which of the associative arrays I want to put this bit of data in based on its key. So then I can spread the load across all of the different things, and hopefully then get a relatively optimal lookup, despite the fact it's a very unoptimal sort of data structure in the first place. So for that, I need to figure out which chain it's in. And having found out which chain it is, I need to be able to get that, and then I need to be able to step down the associative array and lift out the data item, and the code's all there, and it does work. So, but we have some nastiness because we're in the land of C. I just feel I've reached a stage in my life where basically most of the C code I would write, it would just be malloc X amount of void pointer and figure about the details later. it's not a very sane approach, but it's just, I hate memory management in C. It's one of the reasons why I always loathed working in it, even when I was doing a lot of low-level code in it, because it just seems like something a computer should be able to do for me. And we have to go through all the bother of actually initializing all these things so they're null, and it's just, it's prone to potential errors implementing this stuff. Mapping isn't a very interesting, well, working out the map value also isn't very interesting, but one of the things you do get, obviously, is that you could replace map chain, this implementation of it, with a different hashing algorithm. So you can tailor it to the kind of keys or the kind of data or whatever. And that's kind of nice, because we can't do that with maps in Go. We get the map, and it does the hashing, and that's it. But we can do an implementation of that map algorithm in Go. And I put this in because I thought, well, you might as well do it in Go if you can do it in C. So firstly, associative arrays are dead easy in Go, because yet again, we've just got a singly linked list with a couple of items of data in. And the one thing we need to do is, for any cell we look at, we need to be able to lift out the value that goes with a key if the key is actually the key for that cell. That's the one trick that this needs to be able to do. The search is also very easy to write, and it's because we're now working in a place where we can put methods on the structure rather than having to come up with creative names like map underscore whatever. You end up with a much cleaner API when you start using it. I find it much easier to look at this and go, yes, that's stepping through a search, and it's checking it's still searching and all of that, than I do when I've got a whole, and it fits nicer on the screen. So, and then the actual map itself is actually not a very heavyweight bit of code. There was an awful if, else if tangle down here in C, but of course in Go, we can put executable statements there for the cases. So actually, suddenly, the whole thing now looks much easier to read there. I think there's something in there I can abstract out differently, but it's not really worth the effort, because obviously, once we've gone past proving that works, which it does, oh, come on, I just put the slide in. Right, oh, that is the slide. That's me. I forgot to color code, because of course we can just do that. And we don't have to care about what the actual size of the map we're going to use is or whatever. So that's actually really nice. I like that. But basically, we're going to want these two basic data structures at a later point. One to provide stacks to maintain immediate data. The other to provide long-term caches. So that's how we do the caching side. Now, dispatch loops. Oh, please, God. I'm going to overrun by 5 minutes, and I'm going to stop after dispatch loops. And unfortunately, there's a lot of C here, because there's two types of dispatch loop you can't write in Go at present, in straight Go. So the point of a dispatch loop is we're going to fetch something from memory that's an instruction. We're going to decode that instruction, and then we're going to execute that instruction. So normally there'll be a program counter. Yeah. Oh, and the bit down the bottom is important. When we've done an execution, it will have changed the state of the machine. If you want to write one of these, write a VM so it's functional, you can, but essentially every instruction execution then becomes a snapshot, which is perfectly reasonable if you've got a lot of RAM, but it might not necessarily be what you're looking for. So the first off, this is the basic one. If you've ever done any kind of noddy programming languages course, you will have been taught how to do a switch interpreter, because it's the most obvious way to interpret instructions. So you've got a whole chunk of instructions that are stored sequentially in memory. Each is represented by some kind of token or opcode, so this is where we get the word bytecode from, because obviously you can make them bytes. Pretty much every language under the sun can do it, because really all we're doing is creating our own Turing machine that just steps through a tape and says what to do with this bit of the tape now. Nothing more complicated than that. And because it's tokenized, you can end up with a very compact representation, or not, depending on what you want to do. So first we need stacks. It's impossible to do these things without having stacks. So this is just very simple spaghetti cactus stack I've used. And that means I've put in some code for doing a push and a pop. That's completely boring. We need to then have some kind of way of expressing the bytecode. So in C, we've got an enum. I wish there was, this is one thing I would like from C and Go. I'd love there to be able to just put enum statements. I also have something I would steal from Pascal, but that's a whole different talk. Possibly not something anybody else wants either. Interpreting is very simple. We just have an endless loop. We have a couple of registers, which I've called Eleanor for left and right. And then as we step through our program, we just say, well, what's this next instruction? And then we jump to the appropriate case and do it. There are some odd optimizations you can do. One of them is you can sort of shoehorn the Duffy device in, which is an abusive use of the C standard to basically skip to the right place in the wrong way. And I'm not going into that because it makes my head hurt every time I read it, especially in live code, where you don't want to ever meet it. But essentially, we've got this little program. It just runs through. I've lost the things off the side, but basically all it does is it adds together 13 and 20-something or other, 28 probably, and then prints it out and exits the program. But it's a genuine program. We're setting up some state on a stack. We're doing an add. We're doing a print, so we've got I/O. And on top of that, we're exiting, and then we're dropping out of the loop. I'm not belaboring those examples. Obviously, we can do more stuff. We can refactor slightly. We can add different instructions in. Direct call threading is what most day-to-day VM runtimes use until somebody starts to do optimization on them. Direct call threading is a step on from switch interpreters. So we've still got the sequential memory store for instructions. But now, we've got a pointer to a function as opposed to actually having a token that we'll look up in a switch statement. So effectively, we can take the one and we can take a switch interpreter and we can actually use it as a compiler to produce this stream of function calls. It is not available in all languages. You know, we're in the territory now where we're in C-isms. And also, you know, instructions will require a machine word, and if actually the amount of space you've got to do what you want to do in is important, you might want bytes, not words. So yet again, there are good reasons why, even though this is faster, you wouldn't use it. We've got the same boring setup. We've got a stack and stuff. What we've got over here is a rather different loop. We've still got this endless loop, but now we literally just allow the program counter to keep incrementing itself through and through and through and through and through. And you think to yourself, well, that means the program's going to explode. Well, yes, but the program counter is now global. Any one of the function calls can itself manipulate the program counter. So now, an instruction is responsible for figuring out whether or not it should move backwards or forwards in the program. Highly error-prone in all kinds of ways that are interesting. But it's much faster, because now you've taken the switch overhead in C is often ridiculous, depending on the compiler. And now, when we exit the program, we literally just directly exit the program, which is even better. So, boom, 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 let's skip past that. Oh, I've just put some more things in. Right, now indirect threading is the point where my head starts to hurt again. Keeping these things live in your head while you're working on other stuff can be a bit difficult. So, yet again, sequential instructions. In fact, I think possibly all of them using sequential instructions, and I've been highly redundant there. This time, we don't have function calls. We have local jump addresses. We've got a whole set of code as part of the body of the function that's the interpreter. And we've got the addresses. So therefore, we can do jumps straight to that particular label. Now, this used to only be GCC that allowed you to do this, to actually treat a label as a data item, so that you could get the address. Now CLang does since 1.7. I was very pleased to discover, because that meant that all my examples worked on my Mac without my having to install GCC. And this time, instructions are indirectly loaded, or rather, they indirectly load the next instruction. So there's no longer a central loop that runs a program counter. And even more hilarity can arise from that. So we've still got the same setup, only now we've got our program. Our program is actually a whole point of these local jump addresses inside our interpreter to each of these. And then we just started off up here by doing a goto. And then, oops, I wasn't expecting that. And then the gotos just basically feed on to more gotos. It can be actually really fast, and oh, there's a slide here that's kind of fun. I'm just trying to remember where it is. No, perhaps I didn't put it in the slide. Perhaps it's just in the code that goes with the deck. But basically, what you can do is you can then write your own optimizing cache in here to actually compile the local jump addresses. And the first time I actually wrote the code for that, it took up a third of the entire time it took to write the code for this talk, because I kept segfaulting, because I kept forgetting that there's no escape analysis in C, and that therefore when you pass something up the stack, the execution stack, yeah, it's gone out of scope. It doesn't exist anymore. It's an interesting bug to fix, because you look at it and you think, that seems quite reasonable. Oh, it's not. So anyway, and you can do all kinds of stuff with defines, etc. So you can basically build your own little DSL now around the whole interpreting process. Now, direct threading, yet again, makes my head hurt. And this is now the point. This is the example that I was just talking about. I've now got a compiler. This compiler can take a table that's been generated of the addresses of that, which can be passed out, and then it can run off and it can compile an arbitrary program. And then all it has to feed in to do the interpretation is that stream of jump addresses that it's now got, which means you can now have a separation between effectively the bytecode that you're executing, which is the jump addresses, and another bytecode that's the actual portable format you'd use, say an intermediate language or something. And at this point, you now basically can, anything you can build in hardware, you now have 2/3 of being able to do in software, because we're not going to cover the I/O bit, because that's the other bit of the equation you need to fill in. So anyway, so we'll skip past that. It's C, who cares? Oh, go on, there's a Go version. No, there isn't. Of course, that's the point. There's no Go version of either of these. But obviously, there's Go versions of the Switch in the first one. The final thing, because it's not really relevant in most systems programmers think, but it's actually incredibly relevant if you're looking at software as a machine, and that's timing. And I feel really bad showing the code off I'm about to, because I stole it, absolutely gratuitously off of Andrew Gerard. Because he wrote this nice little random number generator using channels. And it turns out that the random number generator using channels is also an incredibly good way of implementing a control clock. So if I've got a processor in the real world, I have clock pulses. Now, I might have a global clock pulse, or I might have local clock pulses per execution unit. It's one of the optimizations people make to cut down on the energy cost of processor. Oh, we turn off 3 cores. That's 3 clock pulses have all turned off as well, things like that. But that clock pulse is providing synchronization across the whole processor. We could, of course, because we're building machines out of components of our own choosing, we can actually have lots of different synchronization going on, but we do need the clock pulse. So I'm going to, it'll all be online. So I'm going to skip past that. There's a whole pile of interesting stuff about how machines work. All right, well, as a workshop, right, we've covered the first hour, and then there's another 2 that have to go after it. That I've got code for, but it's just like if I put the code in, we'd really be deep in it today. The one thing I want to pick up that's actually quite fascinating, there's a kind of way of creating a processor called transport triggering. Now, anybody who's done assembly language, you're used to having a set of instructions, and you load stuff from memory, you do something with it, and you stick it back to memory. Transport triggering is fantastically weird. It doesn't give you instructions. You can only do reads and writes of data. Every single one of the instructions for the machine is actually exposed as its internal bus address for the data to go to. So you write programs in which all you're doing is writing the addresses that you want to send data to and the data you're sending there. It is phenomenally difficult to understand those kinds of processors unless you have a very thick manual and a very strong determination to read a lot of hexadecimal numbers. Because there's just, you know, you can write assemblers assemblers. They're not, they're compilers at that point. They're compiling rather than assembling. Because often you might need to use half a dozen different data writes and reads to actually do an opcode. But it's quite fascinating because it allows you to look at just how far down you can break up things. And the idea that a whole computation is nothing more than a set of read and writes is just, you know, I find that quite fascinating. There are some books out there that take a somewhat different approach than I just have. There's this behemoth called Virtual Machines, which is about all kinds of virtual machines. Several chapters specifically about what we've talked about, which they call process virtual machines. And it's a fascinating read. It has no code in it whatsoever, and it has some diagrams that, this is one of the most difficult books to track down. It was published by Byte in the 1970s, because they had a science fiction writer, Jerry Pournelle, who wrote for them, wrote a weekly column for them, and he was obsessed with Forth. So he somehow managed to convince them to publish a book, because they did a magazine. They weren't really book publishing at all. So they published this book on how to implement threaded interpretive languages, which is basically anything that looks like Forth. And it's a brilliant book, but yet again, there's all this notation. This, if you actually want to play with somebody else's virtual machine at a low level, this is worth tracking down. It hasn't been in print for years. They've never done an updated version, which is why it says diskette included. And I've still got the 3.5-inch diskette somewhere, but nothing to read it with. But basically, it is just a nice read-through of the JVM opcodes, and there's a little assembler that goes with it called Jasmine, so you can actually write assembly language programs for the JVM. I have had a lot of very, very drunken nights out with friends in the VM community, basically who think I know a lot more than I do, because I just remember some of the stuff I read in there. And that by and of itself in that community will get people going, my God, you're not a web dev, let's buy you alcohol. So, and finally, I can never recommend this book enough. It's from the early 90s. Basically, it's how to implement programming languages. It's slightly weird because all the programming languages it implements look like Lisp. Because the author implements a Lisp parser in the first 2 chapters, and then he implements Sassel, ML, cluster, for anybody who's really old, a whole pile of weird languages. He implements them in Pascal with Lisp syntax. And there's horrible math in there as well, all over the place, all this damn set and group theory stuff going on. But all the code is in Pascal and really, really easy to read. And it's even got a nice chapter, 2 intro chapters, one on garbage collection and memory handling, and the other one is an intro chapter on basically, bytecode optimization, how to. And it's just there is somebody actually did a port of all of the 10 interpreters to C. And that's floating around on the internet. But it's of all the I've bought a truckload of computing books over the years, most of which have gone to the pulper within about 2 years. This one, it's one of about half. Well, these 2, amongst half a dozen. That if my house is bombed, I'm grabbing them first. The child hopefully will grab some of the others that are less important and follow me out the door. But you can always have another child. This I'm going to get so much trouble when this actually is online. But anyway, thank you very much. I hope that completely whirlwind, totally nuts attempt at doing a lightning workshop hasn't left you all thinking, how barking mad, I don't want to do this. And I'm around for questions later over food and probably not alcohol, because I got very, very drunk last night. It's a miracle this talk exists. So. Yeah, oh.